Hi everybody, so in this video I want to introduce the notion of what a binomial distribution is, when a binomial distribution would apply to a random variable, and what are some things to look for when we wouldn't want to use a binomial distribution. So let's just begin with an example that we've seen before. So let's consider we are taking a quiz. There are 5 questions on the quiz, which is multiple choice. Each question has 4 possible answers. And let's say we want to consider, if we're randomly guessing on each question, how likely are we to get nothing correct, 1 correct, 2 correct, etc. So first, let's just identify that the random variable x here is going to map an individual outcome. We'll call that omega. It's going to map this to the number of correct guesses. And this random variable is going to follow a binomial distribution for reasons that we'll see below. So the first observation to make here is that we have a fixed number of trials. In this case, each trial is a question. So we have a set number of trials, in this case, 5 of them, from which we can get questions right or wrong. So at total, we're going to have 5 repeated trials. And here we denote the number of trials. We use the notation n. So we would say n is equal to 5 in this example. So the first thing to look for is we have a fixed set number of trials. Next thing is, in each of these trials, it's a binary thing. That's why we get a binomial distribution. There's only 2 possible outcomes that we can get. We're going to consider 1 possible outcome a success and 1 a failure. The success and the failure might not refer to something good or something bad. We're just going to consider the successes, the things that we're counting. So in this case, we're counting the number of correct guesses. So our success would be a correct guess in this case. So we need fixed number of trials. Each trial has 2 possible outcomes that we are considering. And we denote that the probability of a success in any given trial with the letter p. So we use the variable p to denote the probability of a success. And therefore, since there are only 2 possible outcomes, we could calculate the remaining probability would be the probability of a failure. And failure, we typically denote with the letter q, and the relationship is that q is 1 minus p. So if we have a 25% chance of getting the question right, then we have a 75% chance of getting the question wrong. And the last property that you want to make sure, and this is really important, is that each trial is independent from the others. So whether or not I get question 1 correct doesn't affect my odds of getting question number 2 correct or question number 3 correct. So every trial is repeated under identical conditions, and this means that the value of p, the probability of a success, is the same in every single trial. So in this case, we have 5 questions. On each of those questions, we have a 25% chance of getting the question right, and those odds are the same, and those odds don't change based on any of the other trials that we've run. And if a random variable satisfies these 3 properties, then we say it follows a binomial distribution. And again, these 3 properties are, it has to have a fixed number of trials. Each trial has only 2 possible outcomes, and each trial is independent from the other. So as long as our random variable has those properties, then we can use a binomial distribution to calculate some probabilities, to calculate expected values, and so on. So this part we'll talk about in class, how we can use formulas to calculate probabilities of binomial distributions. In this video, I want to focus on how we can identify whether or not a distribution is binomial, and then how we can identify the values for n and p. Once we can do that, then we'll see that technology R is going to be able to calculate these probabilities. So let's consider the following example. You are driving to a friend's house, and there are 3 traffic lights along the way. At each light, green lasts for 30 seconds, yellow is 10 seconds, and red is 20 seconds. And we want to calculate what is the probability, for example, that none of the lights are red on your drive. So first thing here is we'd want to identify why is this a binomial distribution? And recall, we've got three properties that we need to satisfy. So we have one, we need to have a fixed number of trials. And here we can see that there are three lights. So that means that our fixed number of trials is equal to 3. Next, we want to make sure that the probability of success is the same in each of these trials. And so let's think about it. First of all, success here, what is it that we're counting? So we could frame this by thinking about we are going to count up how many red lights do we hit. So we want to calculate the probability that the light is red. That's going to be our success in this case. And we're going to look for what are the odds that we don't get any successes, we don't get any red lights. So here we can take a look and we can see, well, it's green for 30 seconds, yellow for 10, red for 20 seconds. So out of any 1 minute span, that's what this adds up to, 20 seconds out of the 60 seconds, the light is red. So that would be a probability of 1/3. Okay, so 1/3 of the time the light is red, the other 2/3 of the time the light is not red. So one thing that I want to take into account here is that although the light has three possible outcomes, yellow, red, and green, we are considering this we're bunching these outcomes into two. We're going to say not red and red. And so again, red was the success and not red was the failure. So we actually group the green and the yellow together. So you might think this doesn't seem binomial because we have three possible outcomes for the light, but we're considering this as only two. We're considering green and yellow as not red. So we do have two outcomes here. It's either red or it's not red. And the probability that it is red is 1/3. So now, and this is the same in every single light. So we're going to assume here that the probability of getting one light, red, green, or yellow, doesn't affect the probability of the next light and the next light. And since this probability is the same in every trial and each trial doesn't affect the other, this indeed gives us this third property that we need, which is the trials are all independent from each other. So the value of P is equal to 1/3, and here we're considering success of red light. And this would tell us that the value of Q is therefore equal to 2/3. So in this case, we would use a binomial distribution. We have three trials. The probability of success is the same in all three of those trials. And each outcome in a trial is independent of what happens in any other outcome. So here is an example where the random variable counting up how many red lights we hit on this drive would be, the probabilities here do follow a binomial distribution. So let's practice a couple more. If you haven't gotten the hang of this just yet, you want to check to make sure that this is sinking in. So I'm going to go through a couple more examples where we want to determine whether or not we have a binomial distribution, and if so, what are the values for n and p. So if we flip a fair coin 10 times, count the number of times the coin lands on heads, just keep in mind here that a success here would equal the coin lands on heads. We have only two outcomes, heads or not heads, which would be tails. We have a fixed number of outcomes, 10 of them. Probability of success in any one of those trials, since the coin is fair, is 1/2, and any one flip is independent of what happened on all the other flips. So each trial is independent of the other. So here, this is a binomial distribution where n is 10 and p is 1/2. In the second one, we want to count the number of times in a row that a fair coin lands on heads before it lands on tails. And so let's think about what some outcomes might look like in this experiment. So we're going to count the number of times in a row a fair coin lands on heads before it lands on tails. So it's possible it takes one attempt. Our first flip is a tail, and then we would say x is equal to 0 since the coin did not land on any heads before it landed on tails. So in other words, we're counting the number of h's we get before we get our first t. And here's another possible outcome, which would have, we got one head before we got our first tail. And we could get another possible outcome would be head, head, tail, in which case x is equal to 2, and so on. And so if you look at the outcomes that we have here we had one trial, here it took us 2 flips, here it took us 3 flips, and so on. We don't have a fixed number of trials. I can't say we're going to flip the coin this number of times and then count this. The number of flips that it takes is different from outcome to outcome. So in this case, we would say this is not binomial since we don't have there's no fixed number of trials. In number 3, we draw 10 cards from the top of the deck and record the number of cards that are aces. And so for anyone that's not familiar with a standard deck of cards, these are decks that have numbers from 2 up to 10. They have face cards that are jacks, queens, kings, and aces. And each card appears 4 times in a deck. So altogether, a deck has 52 cards. So you can think about it as like a 52-sided die. And we're going to say that 4 cards in the deck are aces. Okay, so out of the 52 cards in the deck, there are 4 aces. So that's pretty much what we need to know about this scenario. So now we're going to pick 10 cards from the top of the deck. And so let's say we pick card number 1. So card number 1, we're going to consider a success here. An ace is picked. And we do have a fixed number of trials here. We're fixing n to be equal to 10. So now let's think about what is the probability of a success in each of these trials. So for card number 1, we have a 4 out of 52 chance. Okay, and now we've picked the first card, and so that means we now have 51 cards left. And how many aces are left in the deck? It depends. Right? We might have 3 aces left in the deck if the first card we picked was an ace, or we might have 4 aces left in the deck if the first card that we picked was not an ace. And what we notice here is, therefore, depending on what we picked with the first card, that's going to affect the odds of picking an ace on the next card. And so either way, this is 4 out of 52. This is 3 out of 51 or 4 out of 51. So in either way, it's different than the probability of success on the first try. And so since each trial is not independent of the other, since when I pick one card out, the remaining deck is now different, the odds have changed, this is not binomial either. And the reason, again, is that these are not independent trials. So out of these 3, just the coin flip experiment was binomial. The second one was not because we didn't have a fixed number of trials. The third one was not binomial because each trial was not independent of the others. So let's take a look at a couple more just to make sure we're comfortable with this. Okay, so in the fourth one, again, we have a standard deck of cards. So we have 52 cards in the deck. And here what we're doing is we're going to pick a card, take a look at what the card is. And one thing that you should know about the standard deck of 52 cards is that there are 4 suits of the cards. So in this standard deck of 52 cards, there are going to be 13 hearts. 13 cards are going to be diamonds. 13 cards are going to be clubs. And 13 cards are going to be spades. So if you're not familiar with the standard deck of cards, here's the most important information we would need about that. So what happens, we pick a card from the deck, and maybe we look at card 1, and we say that card 1 is a heart. And what are the odds of picking a heart? Well, the probability here would be 13 out of 52. And then before we pick the next card, we're going to put our first pick back. So if we pick the heart, we put that heart back in. We pick a second card. And let's say maybe we get a club. And you can think, well, what are the odds of getting that club? There's 13 clubs in the deck. And since we replaced the first card that we picked, there's still 52 cards in the deck. And so we can go on in this process. So the things that are nice to observe here is that we do have a fixed number of trials. We do have independent trials. And here the key is we are replacing the card. Okay, and that is different than the previous example when we were picking the top 10 cards from the deck. In that case, we weren't replacing them, and that's why those events were not independent. When we put the card back in, each time we're resetting the sample space, we're going to have the same probability of picking any one of the suits of the card. But what's not true, okay, remember we're dealing with a binomial distribution, so that means we should have only 2 outcomes. And so here we're counting up 4 different outcomes. We're counting up either the result is a diamond, is a club, is a heart, or is a spade. So we have 4 outcomes. We're not really clear what a success or a failure here is. So the problem here is that we have more than 2 outcomes on each trial. So this right over here is what is going to violate one of the key conditions for a binomial distribution. So this one is not binomial. And lastly, let's take a look at 5. So very similar situation. We have a deck of 52 cards. We're going to pick a card from the deck. We're going to count up how many of these cards are diamonds. And each time we pick, we put the card back in. And so now, right, we're picking 10 cards. Since we're putting the card back, each trial is independent. And so that makes a success here, which is picking a diamond. We're counting how many diamonds we have. So a key distinction to note here is that although we have seemingly 4 different outcomes for the suit, a heart, a diamond, a club, or a spade, we are counting only the diamonds. So in other words, we are separating these outcomes into 2 events. Success is a diamond is picked, and a failure would be not a diamond picked. So here's the situation where although there are 4 different suits, we're thinking about this as a binary outcome where it's either a diamond or it's not a diamond. Each time we pick, we have a 13 out of 52% chance of picking a diamond. And then since we put the card back, it's going to be 13 out of 52 again, regardless of what we picked on the first one. So this one would be a binomial distribution. So for your quiz to take a look at before we meet in class next time, Your goal is to take a look at some descriptions of random variables and determine whether the underlying probability would follow a binomial distribution.